Hello there, and welcome. Tonight I want to take you somewhere far beyond the comfortable boundaries of our everyday world, somewhere that exists in the quiet depths of space where mysteries older than civilization itself continue to whisper their secrets to anyone patient enough to listen. I want to invite you into a journey of wonder and contemplation, an exploration of something truly extraordinary that connects us all to the vast, incomprehensibly beautiful universe that surrounds our small planet. Before we drift deeper into this cosmic mystery together, I hope you'll join me fully on this journey. If you find yourself captivated by the wonders of space and the profound questions that these cosmic phenomena inspire, I'd be genuinely grateful if you'd consider liking this presentation and subscribing to explore more of these contemplative cosmic journeys whenever you have a quiet moment. Your support helps bring these stories of the universe to more people like you who wonder about the mysteries written in the stars. But before we begin our journey in earnest, I'm curious about where you are right now. As you settle in, perhaps with a warm drink beside you or nestled under comfortable blankets, I'd love to know, where in this vast world are you watching from? What time is it where you are? Is it late evening, the witching hour when the night is deepest, or perhaps early morning when the stars are beginning to fade? Are you in a bustling city where the night sky hides behind city lights, or somewhere more remote where the stars can truly speak? Please, share your location and the time in the comments below. There's something deeply connecting about knowing that across different time zones, different continents, different parts of this planet, we're all looking upward together, all wondering about the same cosmic mysteries. We're all part of the same human story unfolding beneath the same stars that have watched over our species for countless generations. Now, let me ask you something that might seem strange at first, something that science fiction writers have warned us about for decades, something that initially sounds almost impossible. What if there existed objects in space so powerful, so magnetically intense, that a single burst of invisible radiation from them could theoretically reach across the vast distances of our galaxy and fundamentally alter everything we know about our world? What if somewhere out there, in the cosmic darkness that surrounds us, there are spinning remnants of dead stars so incredibly dense that a teaspoon of their material would weigh as much as an entire mountain on Earth? These aren't the inventions of imaginative minds, though I understand the skepticism. These are real. They're called magnetars, and they might just be the most fascinating and mysterious objects ever discovered by humanity. You see, it's easy to doubt such things. Our everyday experience teaches us that the universe operates according to rules we understand fairly well. A magnet sticks to a refrigerator. The Earth has a magnetic field that protects us from the solar wind. These are gentle, manageable forces. But then you learn about magnetars, and suddenly you're confronted with a phenomenon so extreme, so far beyond normal experience that it seems almost impossible. And yet, astronomers have observed them. We have real data. We have witnessed their incredible light bursts reaching across impossible distances. The question isn't whether magnetars exist. They do. The question is far more intriguing. Why do they do what they do? What triggers these catastrophic releases of energy? And perhaps most haunting of all, what would happen if one of these stellar monsters decided to look in our direction? It's a question that makes us feel small, admittedly small in a way that can be uncomfortable. But it's also a question that builds gentle intrigue the more you consider it. Because understanding magnetars isn't just about understanding distant cosmic objects. It's about understanding the fundamental nature of reality itself. It's about grasping the extreme conditions that exist in our universe, conditions so different from anything we experience that they challenge our comprehension of physics itself. When we study magnetars, we're studying the universe at its most fundamental level. We're peering into processes that reveal how matter behaves under pressures and magnetic intensities that our minds struggle to conceptualize. And perhaps most importantly, we're asking one of humanity's oldest questions in a new way. What is our place in this vast cosmos? Are we insignificant specks in an indifferent universe? Or are we witnesses to profound mysteries that might help us understand existence itself? This journey we're about to undertake together is one of those rare opportunities to sit with these big questions, to let your mind wander through the cosmic darkness alongside the facts and the mysteries. We'll explore what magnetars are, how they came to be, what we know about their devastating light bursts, And perhaps most intriguingly, we'll examine the possibility, however distant, that one of these objects could affect our world. But here's what I want you to understand right from the beginning. This isn't a journey meant to frighten you. Rather, it's an invitation to wonder. It's an opportunity to experience the profound beauty of a universe so large, so complex, and so mysterious that humanity will likely spend centuries, perhaps millennia, trying to understand it fully. As we settle into this exploration, I want you to imagine yourself in a vast, dark space. Not the emptiness of fear, but the peaceful darkness of a clear night sky far from city lights. Imagine lying back and looking upward, seeing the stars in all their distant glory, knowing that each point of light is a sun like ours, possibly surrounded by worlds of their own. Now imagine in that darkness, there are objects even more remarkable than ordinary stars, objects so extreme that they seem almost impossible, and yet they're there, spinning silently, occasionally flaring with power that rivals entire galaxies. That's where we're going tonight. That's the mystery we're about to explore together. The universe has been full of mysteries since humanity first looked upward and wondered. Ancient peoples created mythologies to explain what they saw in the night sky. Medieval astronomers built elaborate models trying to understand the movements of celestial bodies. Renaissance scientists like Galileo turned telescopes toward the heavens and discovered that reality was far stranger and more wonderful than anyone had imagined. And yet, despite centuries of observation and study, despite the incredible advancement of our technology and our understanding, the universe continues to surprise us. It continues to present us with phenomena so remarkable, so difficult to explain, that even our most brilliant minds find themselves humbled before the cosmic mystery. Magnetars represent this perfectly. They're a relatively recent discovery in the scope of human knowledge. We didn't even know magnetars existed until the 1990s. For most of human history, for all the centuries that our ancestors looked at the stars and created stories about them, magnetars were unknown to us. And yet, they were there, spinning silently, occasionally releasing bursts of energy so powerful that if one were to occur nearby, it could affect our entire planet. It's a humbling thought, isn't it? The universe was doing its thing for billions of years before we even knew these objects existed. And even now, with all our modern technology and scientific understanding, magnetars remain mysterious in many fundamental ways. The discovery of magnetars is relatively recent, but the phenomenon they represent is ancient. These objects are the remnants of massive stars that lived and died long before our solar system even formed. A magnetar might have been created 5 billion years ago, 10 billion years ago, from a star that exploded in a supernova that no human eyes witnessed. It's been spinning ever since, its magnetic field growing more intense with each passing millennium, until it became something so extreme that it defies easy explanation. And then, in the 1990s, our telescopes finally became sophisticated enough to detect them. Our instruments finally became sensitive enough to catch the light bursts these objects occasionally release. Suddenly, we became aware of something that had always been there, something that had always posed a potential threat, something that had always been spinning in the darkness waiting to be discovered. Consider for a moment what this means for how we understand our place in the universe. For most of human history, we believed we were at the center of everything. We watched the stars wheel overhead and assumed they all revolved around us. It took centuries of observation, centuries of mathematical calculation, centuries of brave scientists willing to challenge established beliefs, before we accepted that we're actually on a relatively ordinary planet orbiting a relatively ordinary star in a relatively ordinary galaxy. We're not the center. We're not even particularly special, from a cosmic perspective. And yet, here we are, aware and conscious, able to contemplate our own insignificance. That's almost miraculous, isn't it? We're small, yes, but we're aware. We can think. We can wonder. We can ask questions about objects as extraordinary as magnetars, and magnetars are truly extraordinary. To begin to understand why, we need to think about what happens when a massive star dies. Most stars, when they reach the end of their lives, fade away relatively gently, cooling and contracting as their fuel runs out. But the most massive stars, those that are at least 20 times heavier than our Sun, they don't fade away gently. When their fuel finally runs out, when the nuclear fusion that has held them up against their own gravitational weight finally ceases, something catastrophic happens. The star collapses inward with tremendous force, and then, in a moment of unimaginable violence, it rebounds. It explodes outward in what we call a supernova, a cataclysm so powerful that for a brief time, a single exploding star can outshine an entire galaxy containing billions of other stars. What remains after such an explosion is something almost incomprehensible. The core of the star, which once was perhaps 20 times the mass of our Sun and spanned a distance millions of miles across, collapses down to a sphere only about 12 miles in diameter. All that mass is compressed into a sphere smaller than a major city. The density is almost impossible to visualize. A teaspoon of neutron star material, that's what we call the incredibly dense matter at the core of what's left behind, would weigh as much as Mount Everest. A teaspoon. Imagine holding that in your hand. You couldn't, of course. It would fall right through you, through the floor, through the Earth itself, sinking toward the planet's core due to its incredible density. This is the stuff that magnetars are made of. This is the material we're talking about. It exists in a state that's almost impossible for our minds to truly comprehend. But density alone doesn't make a magnetar special. A neutron star is already incredibly dense, already an object of profound interest to astronomers. What makes a magnetar different, what makes it so remarkable and so mysterious, is its magnetic field. A magnetar possesses a magnetic field so powerful, so intense, that it's fundamentally difficult to describe. Remember when I mentioned that a teaspoon of neutron star material would weigh as much as a mountain? Well, the magnetic field of a magnetar is so strong that if you were to hold up a credit card near a magnetar, if that were somehow possible, which it absolutely isn't, the magnetic field would erase the card from a distance of several hundred kilometers away. The field would rip the iron right out of your blood. It would distort atoms, stretching them into elongated shapes. It would be one of the most hostile environments imaginable. We know these things exist because we've seen evidence of them. We've detected their light bursts. We've measured the radiation they release. And yet, in many fundamental ways, magnetars remain mysterious. We're still trying to fully understand how they work. We're still puzzling over what causes those sudden, catastrophic releases of energy known as magnetar bursts. It's this mystery that we're going to explore together tonight. We're going to think about what we know, what we don't know, and what it all might mean for our understanding of the universe and our place within it. The questions surrounding magnetars are fascinating because they touch on some of the most fundamental aspects of physics. How does matter behave under extreme conditions? What happens to the laws of physics when forces become so intense that our normal understanding breaks down? How do magnetic fields work at scales and intensities that nothing in our everyday experience can prepare us for? These aren't just academic questions. They're inquiries that help us understand the universe at its deepest level. And they're inquiries that magnetar research is helping us answer. When we look at magnetars, we're looking at one of the most extreme natural laboratories that exists anywhere in the cosmos. These objects are conducting experiments in physics that we could never conduct in any laboratory on Earth. They're showing us how matter and energy behave under conditions so extreme that they're almost beyond description. And every time a magnetar releases one of its mysterious light bursts, every time a telescope detects the radiation streaming across space, we have an opportunity to learn something new. We have a chance to understand a little more about how the universe really works, but I'm getting ahead of myself. Before we dive deeper into the mysteries of magnetar bursts and their implications, I want to make sure you're comfortable settling in with me for this journey. If you're still here, if you're still curious about these cosmic mysteries, then I'm grateful. The fact that you're listening to this, that you're willing to spend time thinking about magnetars and the profound questions they raise, that means something. It means you share humanity's oldest impulse, the desire to understand the cosmos. So please, if you're still engaged, if you've found something interesting in what we've discussed so far, I'd love for you to comment below and let me know. What aspect of magnetars intrigues you most? Is it their incredible density? Is it the power of their magnetic fields? Is it the mystery of their light bursts? Is it perhaps the possibility that one could affect our world? Your thoughts matter, and they help guide the conversations we have about these cosmic mysteries. As we continue our journey deeper into the magnetar mystery, I want you to keep one thing in mind. Everything we're about to discuss is grounded in real science. Magnetars aren't theoretical objects that might exist someday. They're not the inventions of science fiction writers, though they certainly deserve to be. They're real. We've detected them. We've studied them. And the more we learn about them, the more fascinating and mysterious they become. The questions surrounding magnetars are real questions that real astronomers and astrophysicists are asking right now, at this very moment, as you sit here listening to this story. One of the fascinating aspects of magnetar research is how recent it all is. Remember, we didn't know magnetars existed until about 30 years ago. That means that within the lifetime of people who are still alive today, we've gone from complete ignorance about these objects to developing sophisticated understanding of their properties. We've discovered that they exist. We've learned how to detect them. We've developed theories about how they form and what they do. And yet, there's still so much we don't understand. There are still mysteries that our best minds are working to solve. It's almost like we've opened a door to a room we never knew existed, and now we're just beginning to explore what's inside. The universe has a way of humbling us, of reminding us that no matter how much we think we know, there are always surprises waiting. Magnetars are one of those surprises. They're objects so extreme, so remarkable, that they deserve our wonder and our careful attention. And tonight, we're going to give them that attention. We're going to think deeply about what magnetars are, how they came to be, what we know about them, what mysteries still surround them, and what it all might mean for our understanding of existence itself. This is the kind of conversation that's best had in the quiet hours, when the world around us is peaceful and our minds are free to wander. This is the kind of mystery that rewards contemplation. So settle in, make yourself comfortable, perhaps dim the lights a bit. The darkness will help you focus on the words and the images they create in your mind. As we move forward together, we'll travel through concepts that range from the scientific to the philosophical, from the concrete to the deeply speculative. We'll consider real observations and real data, but we'll also allow ourselves to wonder about possibilities. We'll maintain scientific rigor, but we'll also maintain a sense of awe and mystery. Because that's really what this is all about. Maintaining that sense of awe and mystery that makes us human. It's the part of us that looks at the stars and asks questions. It's the part of us that's never satisfied with simple answers when there are deeper mysteries to explore. Now, let's begin to understand what magnetars actually are. Let's start from the beginning, from the moment when a massive star is born, all the way through its life and death, until we arrive at the point where a magnetar is born. It's a story that spans billions of years, and it's a story that will help us understand why these objects are so extraordinary. A massive star forms when a cloud of gas and dust collapses under its own gravity. This happens throughout galaxies, including our own Milky Way. In fact, there are regions of space right now, at this very moment, where new stars are being born in exactly this way. A cloud of material collapses, becomes denser and denser, until eventually the pressure and temperature at the core become so great that nuclear fusion ignites. Hydrogen atoms begin fusing together to form helium, and in that fusion process, enormous amounts of energy are released. This energy is what keeps the star shining. This is what lights up the night sky. This is what made it possible for life to evolve on planets like Earth, because stars like our Sun provide the energy source for all biological life that we know of. But stars don't live forever. Eventually, they run out of fuel. The hydrogen in their cores fuses into helium, and in massive stars the process continues. The helium fuses into heavier elements like carbon and oxygen. And the process continues further, with each successive generation of fusion creating heavier and heavier elements, until finally the star reaches a point where it's creating iron in its core. And here's where something crucial happens. Iron fusion doesn't release energy, it consumes energy. At this point, the star can no longer support itself against its own gravitational weight. The core collapses inward, and then, in a moment of unimaginable catastrophe, it rebounds. A shockwave propagates outward through the star, and the entire outer layer is blown away in a thermonuclear explosion. This is a supernova, one of the most powerful events in the universe. What remains is the core. What remains is a neutron star, or in some cases what becomes a magnetar. This collapsed core, this incredibly dense object, continues to spin. In fact, the collapse actually causes it to spin faster, much like a figure skater spins faster when they pull their arms in toward their body. And as it spins, something remarkable happens. The magnetic field of the original star, which was already powerful before the collapse, becomes vastly more intense. The magnetic field lines get compressed into a smaller and smaller space. The result is an object with a magnetic field so powerful that it's almost beyond comprehension. To give you some sense of the scale we're talking about, let me try to paint a picture with numbers. The Earth has a magnetic field. It's what makes compasses point north. It's what protects us from the solar wind. It's a field strong enough to be useful for navigation, and yet from a cosmic perspective, it's relatively weak. Scientists measure magnetic field strength in units called teslas. The Earth's magnetic field is about 50 microteslas. That's 50 millionths of a Tesla. Now compare that to a magnetar. A typical magnetar has a magnetic field of about 10 billion teslas. That's 10 followed by 9 zeros. That's not millions of times stronger than Earth's field. It's not even billions of times stronger. It's quadrillions of times stronger. The numbers become almost meaningless when they get that large. Your mind struggles to even conceptualize what that means. And yet, that's the kind of forces we're dealing with when we talk about magnetars. What happens in such an intense magnetic field? What does reality look like in such an environment? Well, atoms themselves begin to deform. Electrons, normally spread out in cloud-like orbitals around nuclei, get stretched and distorted. The very structure of matter becomes warped. If you were somehow able to exist near a magnetar, which to be clear, you absolutely could not, the magnetic field would rip the iron from your blood. It would stretch atoms into elongated, pencil-like shapes. Your body wouldn't remain a body for very long. The physics would be so extreme that human biology would cease to have meaning. And yet, despite this incredible hostility, magnetars are scientifically fascinating. They're laboratories of extreme physics. They're places where the universe shows us what happens when the laws of physics are pushed to their absolute limits. Every time we observe a magnetar, every time we detect one of its light bursts, we gain information about physics at scales and intensities that we could never recreate in any terrestrial laboratory. In a very real sense, magnetars are teaching us about the fundamental nature of reality itself. The formation of a magnetar is not a common occurrence. It requires a very specific set of circumstances. You need a massive star, at least 20 times the mass of our Sun. This star needs to live its entire life and then explode as a supernova. And the core of that star needs to have the right conditions, the right mass, the right rotation, the right magnetic field to become a magnetar rather than just an ordinary neutron star. So magnetars are relatively rare. In a galaxy like the Milky Way, which contains hundreds of billions of stars, there are probably only a few thousand magnetars. They're rare enough to be special, common enough that several have been discovered and studied. And here's what makes them even more remarkable. We think that a significant fraction of neutron stars might actually be magnetars. We might not have known about magnetars at all if we didn't have sensitive enough telescopes to detect their light bursts and the radiation they release. A magnetar that isn't currently active, that isn't currently producing a light burst or releasing significant radiation, might be almost invisible to our telescopes. So we might be surrounded by far more magnetars than we realize. Right now, in the universe around us, there are probably thousands or millions of magnetars spinning silently in the darkness, some close by in cosmic terms, some unimaginably far away. Most of them are probably inactive, not releasing the dramatic bursts of radiation that make them visible to us, and we know almost nothing about them. This thought leads to a profound sense of wonder, doesn't it? Right now, somewhere out there in the cosmos, there are objects so extreme, so powerful, that a single burst of radiation from them could theoretically affect an entire planet. And many of these objects are completely invisible to us. We don't know where they are. We don't know how close the nearest one might be. We don't know when one might suddenly decide to release a burst in our direction. The universe is full of mysteries, and magnetars are among the most mysterious and most powerful. But let's take a step back for a moment and think about this more carefully. Let's think about what we actually know versus what we're speculating about. Science progresses by careful observation, by gathering data, by testing hypotheses. We know that magnetars exist. We know they have incredibly powerful magnetic fields. We know they occasionally release bursts of radiation. We know the physics of how magnetic fields work. What we don't fully understand, what remains mysterious, is what causes those bursts, what triggers them, what's happening inside a magnetar when it releases one of those catastrophic flares of energy. These are the questions that drive magnetar research. These are the mysteries that keep astronomers working late into the night, analyzing data from telescopes and space missions. The birth of a magnetar, then, is something we can describe in broad terms. It comes from the violent death of a massive star. It's created in the chaos of a supernova explosion. It's born already spinning, already possessing an incredibly powerful magnetic field. From that moment of creation, which might have happened billions of years ago, a magnetar begins its existence as one of the universe's most extreme objects. It spins in the darkness. Its magnetic field reaches out across the space around it, distorting and warping anything nearby. And occasionally, for reasons we're still trying to fully understand, it releases those mysterious bursts of energy that allow us to detect it, that allow us to know it's there, that allow us to contemplate its incredible power. As we sit here thinking about these objects, as we let our minds wander through the cosmic darkness where magnetars quietly spin, it's important to remember that this is real. These aren't hypothetical objects. These aren't thought experiments. Magnetars are out there right now, at this very moment, as real and solid as anything else in the universe. They're products of the same physical processes that created our sun, our planet, and ultimately us. Understanding magnetars is, in a very real sense, understanding something fundamental about ourselves. Because we're made of stardust. The atoms in our bodies were created in stars or in the supernovae that mark their deaths. And magnetars, while they're not common, are nonetheless part of the cosmic ecosystem that made our existence possible. The universe created these objects for no particular reason. There's no grand design, no intention, no purpose to their existence except that the laws of physics create them as a natural consequence of massive star formation and death. And yet, here we are, aware and conscious, able to contemplate their existence, able to ask questions about them, able to wonder about what they mean. That's almost miraculous. That's the kind of thing that makes existence feel precious and meaningful, even in the face of cosmic mysteries that are almost incomprehensibly vast. So as we move forward in our journey tonight, as we continue to explore magnetars and their mysteries, hold this sense of wonder close. Hold the awareness that you're thinking about real objects in a real universe, objects so extreme that they challenge our understanding of physics itself. Let your mind wander through the possibilities, but also stay grounded in the facts, in what we actually know, because the truth about magnetars is actually far more interesting than almost any fiction we could imagine. The discovery of magnetars was itself a fascinating chapter in the history of astronomy. For decades, astronomers knew about neutron stars. These objects were predicted theoretically before they were observed, which is remarkable in itself. Scientists worked out the mathematics, realized that such objects should exist, and then later, observers found evidence of them in the form of pulsars, neutron stars that spin so rapidly they send out beams of radiation like a lighthouse, sweeping across space and occasionally pointing toward Earth. But magnetars were different. They weren't pulsars. They behaved in ways that didn't fit the standard neutron star models, and so, gradually over years of observation, astronomers came to realize that a special category of neutron star existed, the magnetar, an object with a magnetic field so powerful that it changed everything about how such an object behaved. The first magnetar was identified in 1992, when astronomers detected a burst of X-rays from a source they were monitoring. The burst didn't match what they expected from an ordinary neutron star. The energetics were wrong, the timing was wrong, the characteristics of the radiation were wrong. And so, astronomers began to develop a new model. What if this object had a magnetic field that was extraordinarily powerful? What if that powerful magnetic field was somehow involved in the energy release? The model fit, the mathematics worked, and slowly other observations accumulated that supported this new understanding. By the early 2000s, magnetars had become established as a recognized class of astronomical objects, and yet, even as magnetars became accepted by the astronomical community, they remained profoundly mysterious. We could observe them, we could measure their properties, we could work out the basic physics of how magnetic fields of such intensity would behave. But the fundamental question remained unanswered. What causes a magnetar to suddenly release an enormous burst of energy? This is the central mystery that we're going to explore in depth as our journey continues. Think about it for a moment. A magnetar is spinning in space, perhaps not emitting much radiation at all, relatively quiet, invisible, unless you're looking carefully with the right instruments. And then, suddenly, in an instant, it releases a burst of energy so powerful that it could be detected from across an entire galaxy. What triggers this? What causes a relatively stable object to suddenly erupt? Is it a shift in the magnetic field? Is it a starquake? A sudden fracture in the crust of the neutron star similar to earthquakes on Earth? Is it something we haven't thought of yet, some process unique to magnetars that our current physics doesn't have a good framework for understanding? These are real questions that astronomers are actively investigating right now. The mystery of magnetar bursts is exactly the kind of mystery that draws many people to science. It's something we don't fully understand. It's something that could have profound implications if we did understand it. It's something that connects us to people all around the world who are equally fascinated by trying to solve this puzzle. When a magnetar releases a burst, when one of our space telescopes detects that burst, information about that event is rapidly shared throughout the global astronomical community. Scientists gather together, either physically or virtually, to analyze the data. They publish papers. They propose new theories. They conduct experiments and observations designed to test their ideas. It's a beautiful example of human curiosity in action, of the scientific process at its best. And as we think about all of this, as we contemplate these objects so distant and so different from our everyday experience, we should recognize that we're participating in something profound. We're participating in humanity's ongoing quest to understand the universe. We're extending a tradition that goes back thousands of years to the first humans who looked at the stars and wondered what they were, what they meant, how they worked. We're part of that same impulse. We're sitting in the darkness, looking outward, wondering about the cosmos, and that's beautiful. That's what makes us human. Now, having set the stage, having explored the context in which magnetars exist and how they came to be discovered, we're ready to dive deeper into the specific mystery that defines them. We're ready to think carefully about their incredible power, about their devastating light bursts, about what we know and what we're still trying to discover. But before we move into that deeper exploration, I want to pause here and check in with you again. If you're still with me, if you're still engaged with this cosmic mystery, I'd genuinely love to hear from you. What have you found most interesting so far? Is it the sheer scale of magnetars' power? Is it the fact that they're real objects that we can actually observe? Is it the mystery of what causes their bursts? Is it simply the wonder of contemplating something so extreme that it exists at the very edge of our understanding? Please take a moment and share your thoughts in the comments. Your engagement helps this conversation continue, and it reminds us all that we're not alone in our cosmic curiosity. And so we continue our journey deeper into the mystery, deeper into the darkness where magnetars spin their silent vigil over the universe. The journey to understand what makes magnetars truly unique, what separates them from other neutron stars and makes them so remarkable, requires us to think carefully about magnetic fields themselves. We experience magnetism in our daily lives. We use magnets to hold notes on refrigerators. We use the Earth's magnetic field to navigate. We have a basic intuitive understanding of how magnets work. But this intuitive understanding, while useful in everyday life, completely breaks down when we try to think about magnetar-strength magnetic fields. The numbers become so large, the intensity becomes so extreme, that our brains struggle to even process what we're talking about. Let me try a different approach to help you understand. Imagine the magnetic field of Earth. It's a real, measurable force. You can literally feel its effects if you hold a compass. This field is created by the movement of liquid iron in the Earth's core. It extends out into space around our planet, and it protects us from dangerous radiation from the sun. Without Earth's magnetic field, life as we know it probably wouldn't exist on our planet. And yet, compared to a magnetar, Earth's magnetic field is almost negligible. If you took the most powerful electromagnet ever created by human civilization, if you took the strongest magnetic field we've ever generated in any laboratory, it would still be many, many times weaker than the field of a magnetar. We simply cannot recreate magnetar-strength magnetic fields with any technology we currently possess or can foresee possessing. This brings us to a fascinating question. What does space actually look like near a magnetar? What does reality become when magnetic forces reach such intensity? Well, the mathematics of electromagnetism tells us some disturbing things. The field is so strong that it begins to warp space-time itself. Einstein's theory of general relativity tells us that massive objects curve space-time around them. Well, the intense magnetic field of a magnetar curves space-time in its own way. The physics becomes so extreme that it enters the realm of what physicists call strong field gravity, conditions where relativistic effects become crucial, where Newtonian physics completely breaks down, where we're operating at the very edge of our theoretical understanding. Matter itself behaves strangely near a magnetar. Atoms get stretched and distorted by the magnetic field. Electrons, which normally have a certain amount of freedom to move around in their orbitals, get constrained and flattened. If you somehow managed to bring an ordinary atom near a magnetar, it wouldn't remain ordinary for very long. The field would reshape it, transform it into something completely different, something that ordinary chemistry couldn't describe. But perhaps most remarkably, the intense magnetic field of a magnetar actually affects the vacuum of space itself. Quantum field theory tells us that the vacuum, the seemingly empty space between objects, isn't actually empty. It's filled with quantum fluctuations, with virtual particles constantly popping in and out of existence. A magnetar's field is so intense that it actually affects these quantum processes. It distorts the vacuum itself, creating conditions so extreme that the normal rules of quantum mechanics start to break down. This is the frontier of theoretical physics, the place where our best current theories start to struggle. All of this helps us understand why magnetars are so profoundly mysterious and so fascinating. They exist in a regime where our physics is barely adequate to describe them. They're challenging us to develop better theories, deeper understandings of how the universe really works at the most fundamental level. Every observation of a magnetar provides us with data that helps us refine our theories, helps us understand the universe better. And every mystery we encounter with magnetars pushes us to think deeper, to ask better questions, to develop our scientific understanding. The incredible power of a magnetar's magnetic field is actually part of what allows us to detect them. If a magnetar had a magnetic field that was merely strong but not extraordinarily powerful, it might be essentially invisible to our telescopes. It would spin in the darkness, and we would never know it was there. But because the field is so powerful, because it reaches into the space around the magnetar and distorts and energizes matter in its vicinity, it creates observable effects. It powers the light bursts we can detect. It shapes how particles interact near the magnetar. It makes itself known through the radiation it generates. In a sense, the very intensity that makes magnetars so difficult to understand is also what allows us to study them. And there's something almost poetic about that, isn't there? These objects are so powerful that they're almost impossible to understand, and yet that same power is what reveals them to us. Without their incredible magnetic fields, they would be invisible. They would exist in the darkness, unknown and unseen. But because they're so extreme, we can detect them. We can measure them. We can contemplate them. It's one of those beautiful paradoxes of the universe. The very thing that makes something difficult to understand is also the thing that makes it visible to us. As we continue our journey tonight, keep this perspective in mind. We're not just studying distant abstract objects. We're studying real things in the universe, things that have observable properties we can measure. The physics is challenging, yes. The mysteries are profound, yes. But it's all grounded in observation, in measurement, in data that we can actually acquire through our telescopes and space missions. That's what makes it real. That's what makes it more than speculation or pure theory. And that reality is what makes it worthy of our careful attention and our wonder. And so, as we move deeper into our understanding of magnetars, we find ourselves confronted with the central mystery that defines these extraordinary objects. We've established what they are. We've explored how they form from the death of massive stars. We've marveled at the intensity of their magnetic fields, fields so powerful that they reshape the very nature of matter and space around them. But now we come to the question that truly captivates astronomers and astrophysicists around the world. Why do magnetars release those sudden, catastrophic bursts of light and radiation? What triggers these events? What's happening inside a magnetar when it decides, seemingly without warning, to unleash energy equivalent to what our sun will produce over the course of thousands of years? This is the central mystery, the puzzle that keeps scientists awake late into the night, analyzing data from space telescopes, running computer simulations, proposing new theories and testing them against observations. When a magnetar releases one of these bursts, it doesn't release energy gradually or continuously. Instead, energy builds up somehow, in ways we're still trying to understand, until finally something gives way, and tremendous amounts of energy are released all at once. It's almost like a cosmic earthquake, a sudden violent release of pent-up stress that's been accumulating deep within the magnetar's structure. To help you understand what might be happening, imagine the crust of a magnetar. Remember, we're talking about the solid, rigid outer layer of a neutron star. This crust is made of matter in a state that doesn't exist anywhere on Earth. The pressure is so intense that electrons are forced down into protons, creating neutrons. The density is unimaginable. A teaspoon of this material would weigh more than all the humans on Earth combined. And this crust, despite being made of matter so dense and so strange, still has some of the properties of solid material. It can deform, it can stress, and just like the Earth's crust, which occasionally shifts and breaks, releasing energy in the form of earthquakes, a magnetar's crust can also undergo sudden catastrophic shifts. These shifts are what some scientists believe cause magnetar bursts, a magnetar starquake, we might call it. The intense magnetic field of the magnetar is woven into the structure of the star itself. The field lines permeate the crust, running through the material, exerting forces on it. Over time, as the magnetar continues to spin, subtle changes occur in the internal structure. Stress builds up in the crust. The magnetic field pushes and pulls on the material. Stresses accumulate, and then suddenly, something gives. A section of the crust fractures. The magnetic field reconfigures. Energy is released in a violent burst. When this happens, when a magnetar starquake occurs, the results are dramatic. The sudden movement of material in the crust causes disturbances in the magnetic field. These disturbances propagate outward through the magnetosphere, the region of space around the magnetar dominated by its magnetic field. The disturbances cause particles to accelerate to tremendous speeds. Electrons and other particles are energized by the rearranging magnetic field, and as these particles move through the field, they emit radiation. Lots of radiation. Enormous amounts of radiation. In a matter of seconds, a magnetar can release as much energy as our sun will produce in millions of years. All of that energy comes flooding out as X-rays and gamma rays, the most energetic forms of light in the universe. Now this is the theory, or at least one major theory, for how magnetar bursts might work. But here's the thing, we're still not entirely certain this is correct. We're still puzzling over the details. We have observations of magnetar bursts. We have data. But translating that data into a complete understanding of what's really happening is proving to be one of the great challenges of modern astrophysics. The problem is that magnetars are so extreme, so far outside our normal experience, that our intuitions and our conventional models don't work well. We have to think creatively. We have to develop new theoretical frameworks. We have to be willing to challenge our assumptions. Consider this. We've never seen a magnetar burst up close. We've never had a spacecraft anywhere near a magnetar. The nearest known magnetar to Earth is still thousands of light years away. Everything we know about magnetar bursts comes from observations made by space telescopes, instruments orbiting Earth or positioned elsewhere in the solar system, detecting the radiation that travels across the vast distances of space. These telescopes are incredibly sophisticated. They can detect incredibly faint signals. But there are limits to what we can learn from observations made from such enormous distances. It's like trying to understand the internal structure of a thunderstorm by observing it from across an ocean. You can see the lightning flashes, you can measure the energy released, you can study the radiation produced, but you can't see the detailed internal processes that cause the lightning. You can't place instruments inside the storm to measure exactly what's happening. You're working with incomplete information, and yet, despite these limitations, scientists are making remarkable progress in understanding magnetars. Every burst that's detected, every piece of data that's gathered, adds to our knowledge. Slowly, piece by piece, we're building a more complete picture of how these extraordinary objects work. One of the fascinating aspects of magnetar research is how it connects to other areas of astrophysics and physics. The study of magnetar bursts has implications for our understanding of magnetic reconnection. a process where magnetic field lines suddenly rearrange, releasing energy. This same process is thought to occur in the Sun's atmosphere, causing solar flares. It occurs in the Earth's magnetosphere, causing auroras and geomagnetic storms. So understanding magnetars helps us understand these processes in contexts closer to home. Conversely, studying magnetic reconnection in Earth's magnetosphere or on the Sun gives us insights that might apply to magnetars. It's a beautiful example of how different areas of science inform each other, how understanding one thing helps us understand another. The variety of magnetar bursts is itself interesting. Not all magnetar bursts are the same. Some are smaller events, releasing relatively modest amounts of energy. Modest, that is, compared to the catastrophic events. Other bursts are truly enormous, releasing so much energy that they overwhelm our instruments. Some bursts show structure. They have features that suggest complex processes occurring inside the magnetar. Other bursts appear relatively simple. Some magnetars burst frequently, releasing multiple events in a single day. Others might go quiet for years or decades between bursts. Each magnetar seems to have its own personality, its own patterns. Understanding why different magnetars behave differently, why the same magnetar can exhibit different types of bursts, is part of the ongoing puzzle that astronomers are trying to solve. The observation of magnetar bursts presents special challenges for space telescopes. X-ray and gamma-ray telescopes, the instruments that detect magnetar bursts, are optimized for looking at specific regions of sky. They can observe a certain area in detail, but a magnetar burst can occur suddenly, without warning. If a burst happens in a region of sky that no telescope is currently observing, we might miss it entirely. Or a burst might be so intense that it overwhelms the detectors, saturating them with photons, making it difficult to extract detailed information about the event. Scientists have had to develop clever strategies to deal with these challenges. Networks of space telescopes have been established so that when one detects a burst, others can quickly reorient to observe the same source. Rapid communication systems have been set up so that when a burst is detected, the information is immediately shared with the global astronomy community, allowing others to make observations quickly. This international cooperation in the face of a cosmic mystery is itself worth contemplating. When a magnetar burst is detected, astronomers in different countries speaking different languages, from different institutions and different cultures, all come together to analyze the data. They share information freely. They collaborate without thought to national boundaries or institutional rivalries. In that moment, they're united by a common purpose: to understand the universe, to solve the puzzle, to unlock the secrets that a magnetar has just revealed. It's one of the most beautiful aspects of science, this transcendence of borders and differences in the face of cosmic mystery. It reminds us that humanity can come together when confronted with something larger than ourselves. The instruments that detect magnetar bursts are themselves remarkable achievements of engineering and physics. The space telescopes that observe these events have to be incredibly sensitive. They have to be able to detect individual photons, individual particles of light, arriving from objects billions of light years away. They have to withstand the harsh environment of space, functioning without repair or resupply for years. They have to be sophisticated enough to gather detailed information about the events they're observing, yet simple enough to be reliable and not prone to failure. Building such instruments requires decades of planning, millions or billions of dollars, and the work of hundreds or thousands of scientists and engineers. And the dedication of all these people, all this effort and expense, is driven by the simple human desire to understand how the universe works. When we contemplate magnetar bursts, when we think about the energy release, the radiation that spreads out through space, it's important to remember the scale we're dealing with. A single magnetar burst can release more energy than our sun will produce in its entire lifetime. Let me say that again. In a matter of seconds, a magnetar can release more energy than our sun will produce over billions of years. The sun has been shining, producing energy through nuclear fusion, for about 4.5 billion years. Our sun will continue to shine for another 5 billion years or so. During that entire 10 billion year lifespan, our sun will produce a certain total amount of energy. A magnetar can release that same amount of energy in a few seconds. When you think about numbers like that, when you try to grasp the meaning of them, your mind struggles. The scale is simply too large. The disparity is too great. We use these numbers to try to convey the magnitude of what we're talking about, but the numbers themselves almost lose meaning. They become abstract, divorced from any intuitive understanding. And yet, these aren't exaggerations, these are estimates based on real observations, based on measurements of the radiation that reaches our telescopes. The energy is real, the power is real. The devastation that would result if such an event occurred near Earth would be real. But here's where I want to be careful about the language I use. I don't want to frighten you. That's not the purpose of this exploration. Yes, magnetar bursts release enormous amounts of energy. Yes, they're among the most powerful events in the universe. Yes, if one occurred nearby, the effects could be catastrophic. But magnetars are far away. The nearest known magnetar is thousands of light years distant. The probability of a magnetar burst affecting Earth, while not literally zero, is so small that it's not a practical concern for our immediate future. We're not in danger from magnetars. We're safe. The universe is vast, and magnetars, while powerful, are scattered thinly through that vastness. So we can contemplate magnetar bursts with a sense of wonder rather than fear. We can think about them as remarkable examples of the universe's power and strangeness. We can use them as a lens through which to understand the cosmos. We can be grateful that they exist, that they give us the opportunity to study extreme physics, rather than anxious about them. This is the proper frame of mind for exploring cosmic mysteries, curious, engaged, wondering, but not afraid. The universe is vast and often strange, but it's not hostile to us. We're part of it. We're made of the same atoms that make up magnetars. We're governed by the same laws of physics, and that connection, that deep kinship with everything in the cosmos is something to appreciate. Now, the question of what triggers individual magnetar bursts, while important, is not the only mystery surrounding these objects. There's a deeper question that frames all the others. What is the overall structure of a magnetar? What does the interior look like? We know something about the outer crust, the solid, rigid layer of incomprehensibly dense matter. But what about the layer beneath that, and the layer beneath that? How does the density increase as you go deeper into the magnetar? How is the magnetic field distributed throughout the interior? What role does the liquid outer core play? What about the solid inner core? These are questions that are addressed through computer simulations and theoretical models. Scientists build mathematical models of magnetars, incorporating what we know about nuclear physics, about the behavior of matter under extreme pressure, about how magnetic fields work. They run these models on supercomputers, exploring how magnetars should behave according to our current understanding of physics, and then they compare the predictions of these models to the observations we actually make. When there's agreement between prediction and observation, it increases our confidence that our model is correct. When there's disagreement, it signals that something is wrong with our understanding, that we need to refine our models or perhaps develop entirely new ones. The interior structure of a magnetar is particularly mysterious because we can't directly observe it. We can only infer it from the observable effects it has. It's rather like trying to understand the structure of Earth before we had seismographs. Ancient people could observe Earth's surface, but they had no idea what the interior was like. They might have speculated, but there was no way to know. Eventually, when seismographs were developed, when we could analyze how earthquake waves travel through the Earth, we learned that Earth has a layered structure, a crust, a mantle, an outer core, an inner core. Each layer has different properties. Each layer plays a role in how the Earth as a whole behaves. Similarly, scientists are trying to work out the structure of a magnetar by analyzing how it behaves, how it responds to internal stresses, how it produces the bursts we observe. The magnetic field distribution throughout the magnetar is particularly important, because the field is what's driving the burst events. A magnetar is not just a ball of matter, it's a ball of matter permeated by an intense magnetic field. The field and the matter are intimately connected. The field exerts forces on the matter affects how the field behaves. The two are inextricably linked. Understanding the magnetic field structure of a magnetar is complicated by the fact that magnetic fields are invisible. We can't see them. We can only infer their presence and structure from their effects. A magnetic field exerts forces on charged particles. If we see charged particles being accelerated in certain directions, we can infer the presence of a magnetic field. If we see light being polarized, if we see the orientation of the light waves being changed in a certain way, we can infer the presence of a magnetic field. but inferring the three-dimensional structure of a complex magnetic field from these indirect observations is a sophisticated challenge that requires both skilled observational work and advanced theoretical analysis. One of the remarkable tools that scientists have developed for studying magnetars is something called a gravitational lensing. This is a phenomenon predicted by Einstein's theory of general relativity. According to relativity, massive objects curve space-time around them, and this curvature can bend light rays just like a lens bends light. If a massive object passes in front of a more distant light source, from our perspective, the light from the distant source gets bent and magnified. We can see multiple images of the same object, or see it magnified, or see it in unusual configurations. For magnetars, this effect is usually too subtle to be useful for direct observation. But the principle that massive objects bend light is important for understanding how massive, dense objects like magnetars interact with their environment. The magnetic field of a magnetar is similarly interesting because it extends far beyond the physical boundary of the star itself. The magnetosphere of a magnetar, the region of space dominated by its magnetic field, extends millions of kilometers into space. Matter caught in this magnetosphere is affected by the field. Particles are accelerated and energized, radiation is produced, and this radiation, streaming outward into space, is what we detect with our telescopes. In a sense, a magnetar is more than just the physical star itself. It's also the field surrounding it, the magnetosphere, the region of space where the magnetar's influence extends. Understanding the whole system requires understanding both the star and its magnetosphere, and yet, despite the complexity, despite the layers of mystery, despite the challenges of studying objects so distant and so extreme, progress is being made. Every year, new observations of magnetars are made, new data is gathered, new theoretical models are developed and tested. Slowly, piece by piece, we're building a more complete understanding of how magnetars work. It's the kind of scientific progress that happens gradually, quietly, without fanfare or public attention. It's not the kind of discovery that makes headlines or captures public imagination, but it's real progress, it's meaningful progress, and it's progress that will eventually lead to deeper understanding of the universe and the extreme physics that plays out in the cosmos. If you're still engaged with me, still thinking about these cosmic mysteries, I want to check in with you again. What has stood out to you so far? What aspects of magnetars have captured your imagination or sparked your curiosity? Is it the mystery of what triggers the bursts? Is it the incredible density and magnetic field strength? Is it the international cooperation required to study them? Is it something else entirely? I'd love to hear your thoughts. Please take a moment and share in the comments. Your engagement helps me understand what aspects of cosmic mysteries are most meaningful to people. It helps guide the direction of future explorations, and it reminds us all that we're not alone in our fascination with the universe and its mysteries. As we continue deeper into our journey, we're going to shift focus slightly. We've spent time understanding what magnetars are, how they form, what we think causes their bursts. Now we're going to look at the evidence more carefully. We're going to examine the actual observations that astronomers have made. We're going to look at specific magnetars that have been studied in detail. We're going to consider what the data actually shows us, and we're going to explore how scientists interpret that data. This is where the mystery becomes more concrete, more grounded in observation and measurement. This is where speculation gives way to evidence, though the mysteries remain profound. The first magnetar to be discovered and studied in detail was something called SGR 1900+14. This object burst into prominence, quite literally, with a dramatic burst of radiation on August 27, 1998. On that date, a powerful burst of radiation was detected by multiple space telescopes. The event was so energetic that it actually caused a slight perturbation in Earth's ionosphere, the layer of charged particles in our upper atmosphere. This gave scientists immediate confirmation that the event was real, that it had actually released an enormous amount of energy. In the hours and days following the burst, astronomers around the world trained their telescopes on the direction from which the burst had come. They detected the magnetar itself, observed the radiation it was continuing to emit, gathered data that would help them understand this extraordinary object. SGR 1900+14 has been the subject of intense study since that initial burst. Astronomers have observed thousands of smaller bursts from this magnetar over the years, They've measured its magnetic field strength. They've studied the patterns of its burst activity. They've tried to understand what's special about this object, what makes it behave the way it does. And SGR 1900+14 has become one of the best studied magnetars, giving us more information about magnetars in general than we could have obtained from any other single source. Another famous magnetar is SGR 1806-20. This object is notable for producing what's called a giant flare in 2004. A giant flare is a particularly energetic type of magnetar burst. This particular flare released so much energy that if it could somehow be converted to usable electricity, it would provide enough power for all of human civilization for hundreds of thousands of years. And yet, because the magnetar is so distant, about 50,000 light-years away, by the time the radiation from that burst reached Earth, it was spread over such a vast area that the actual intensity of radiation hitting Earth was modest. Our atmosphere and magnetic field easily protected us from any effects. But had a magnetar burst of that magnitude occurred closer to us, the effects could have been much more significant. These specific examples, SGR 1900+14, SGR 1806-20 and others, provide us with real data to study. They give us the opportunity to test our theories and refine our understanding. Every observation is a piece of the puzzle. Every burst carries information about the internal structure and dynamics of the magnetar. Scientists carefully analyze this data, looking for patterns, looking for clues about what's happening inside these extraordinary objects, and with each new observation, each new piece of data, our understanding deepens. The analysis of magnetar burst data involves sophisticated mathematics and physics. When an observation is made, the raw data from the telescope is carefully processed. Scientists look at the light curve of the burst, a graph showing how the intensity of radiation changes with time during the event. They analyze the spectrum of the radiation, the breakdown of how much energy is present at different wavelengths. They look for periodicities, patterns that might repeat. They search for sudden changes or transitions. Each of these pieces of information tells us something about what was happening in the magnetar when the burst occurred. One of the fascinating discoveries from analyzing magnetar bursts has been the observation of quasi-periodic oscillations, or QPOs. These are rapid oscillations in the intensity of the radiation emitted during a burst. The brightness goes up and down at a regular rate. The frequency of these oscillations can tell us something about the physical size of the region where the oscillations are happening. If the oscillations are rapid, happening hundreds of times per second, then they must be occurring in a relatively small region, because there's a limit to how fast something can oscillate based on its size. The relevant physics here involves the speed of light. No information can travel faster than light, so if you have an oscillation happening over a region the size of, say, 10 kilometers, the oscillation can't happen faster than the time it takes for light to travel 10 kilometers. By measuring the frequency of QPOs in magnetar bursts, scientists can estimate the size of the region in the magnetar where the burst is being generated. This gives direct information about the internal structure of the magnetar. Finding these oscillations was like discovering fingerprints in a burglary investigation. It gives us specific quantitative information about the system. The oscillations are telling us something real about how the magnetar's interior is structured and how it's behaving during a burst. And as we've found oscillations in more and more magnetar bursts, as we've analyzed them in detail, patterns have emerged. Different magnetars seem to have characteristic oscillation frequencies. The same magnetar might show different oscillation frequencies in different bursts, or the frequency might change over the course of a single burst. All of this information is feeding back into our theoretical models, allowing us to refine and improve our understanding of how magnetars work. The technology that allows us to detect and analyze magnetar bursts has improved dramatically over the decades. The space telescopes available today are far more sensitive, far more capable than those available when magnetars were first discovered. New telescopes being built right now will be even more capable still. And this improvement in technology means that the data we can gather is increasingly detailed and increasingly valuable. It means that mysteries that were opaque 20 years ago are beginning to become clearer. It means that new mysteries, hitherto unknown, are being revealed. Consider the James Webb Space Telescope, which just recently began operations as this conversation is happening. This telescope, named after the former NASA administrator who oversaw the Apollo program, is the most sophisticated space telescope ever built. It can observe in wavelengths ranging from visible light to infrared. While it's not primarily designed to observe magnetar bursts in the gamma-ray and X-ray region that previous telescopes focused on, it can still contribute to magnetar studies in various ways. And in the future, new space telescopes specifically designed to observe high-energy radiation from magnetars will be launched. These telescopes will gather data that current instruments can only dream of. They will open new windows on magnetar phenomena. They will reveal details that we currently cannot perceive. This is one of the great ongoing stories of astronomy and astrophysics. The constant push to build better instruments, to gather better data, to observe the universe with greater clarity and sensitivity. It's a process that's been ongoing for centuries, from the first telescopes that Galileo turned toward the sky, through the great observatories of the 19th and 20th centuries, to the space telescopes of today and tomorrow. And this constant improvement is what allows our understanding to advance. Every new telescope, every new instrument, every new technique for gathering data or analyzing it adds to our knowledge and helps us understand the cosmos more completely. The study of magnetars also connects to the broader field of neutron star research. Neutron stars are in general fascinating objects. They're the remnants of supernova explosions. They're places where the normal rules of physics break down. They have gravitational fields so intense that if you were to drop an object from a height of 1 meter onto a neutron star's surface, by the time it reached the surface it would be moving at a significant fraction of the speed of light. The gravitational acceleration near a neutron star is incomprehensibly intense, and yet neutron stars can be studied and observed. There are hundreds of them known to astronomers. They come in different varieties: pulsars, magnetars, isolated neutron stars that aren't part of a binary system, and others. Each type has its own fascinating properties and its own mysteries. Magnetars are, in some sense, the most extreme variety of neutron star. They have the strongest magnetic fields of any known objects. They have some of the most dramatic and violent phenomena occurring in their vicinity. And they challenge our theoretical understanding more than any other type of neutron star. This is one of the reasons that magnetar research is so important and so active. Every advance in understanding magnetars is an advance in understanding the extreme physics that occurs in the universe. Every mystery solved about magnetars is a step toward deeper understanding of how matter and energy behave under the most extreme conditions imaginable. The question of how common magnetars are is itself interesting. We know they exist. We've discovered several dozen of them. But how many magnetars are there actually in the Milky Way galaxy? How many are likely in the universe as a whole? This is something scientists try to estimate based on the number of magnetars we've actually detected and assumptions about how many more might exist but haven't been detected yet. Current estimates suggest there might be tens of thousands of magnetars in the Milky Way alone. Many of them might be relatively inactive, not currently producing the bright bursts that make them visible to our telescopes. They might be essentially invisible unless they suddenly decide to erupt. There could be a magnetar relatively nearby, in cosmic terms meaning within a few hundred light years, that we simply haven't detected yet because it hasn't had an active burst recently. This thought is both humbling and fascinating. The universe around us is populated with objects so extreme that they dwarf anything we could ever construct or understand through direct experience. Many of these objects are probably unknown to us. We're constantly discovering new things, constantly revising our understanding of what's out there, and each discovery opens new questions, new mysteries to explore. The universe is inexhaustibly strange, inexhaustibly wonderful. No matter how much we learn, there's always more to discover, always more to wonder about. As we move forward in our exploration, as we consider what magnetar bursts might mean for Earth and for humanity, keep this sense of wonder and this acknowledgement of our limited understanding in mind. We're exploring mysteries that humanity has only recently become aware of. We're trying to understand objects and processes so extreme that they barely fit within our current theoretical frameworks. We're pushing at the boundaries of what we know, trying to expand those boundaries, trying to understand more. It's humbling work, it's challenging work, but it's also profoundly meaningful work. Because through it, we're deepening our understanding of the universe that we're part of, and that understanding, that knowledge, that connection to the larger cosmos is something precious. If you're still here with me, still following along on this cosmic journey, I'm grateful. This isn't light entertainment. This isn't something designed to be quickly consumed and forgotten. This is material meant for contemplation, meant for allowing your mind to wander through cosmic mysteries in a peaceful, meditative way. It's meant to be savoured slowly, to be thought about carefully, to inspire wonder and curiosity. So if you're still engaged, if you've made it this far, you're already part of something meaningful. You're part of humanity's ongoing quest to understand the cosmos, and that's beautiful. That's worth celebrating. Before we move forward to consider the implications of magnetars for Earth and humanity, I want to acknowledge something. In our exploration so far, we've covered a lot of ground. We've thought about the formation of magnetars from the deaths of massive stars. We've contemplated their incredible magnetic fields and the extreme physics that occurs in their vicinity. We've examined the mystery of magnetar bursts and considered the evidence that astronomers have gathered through careful observation. We've recognized that despite significant progress, many mysteries remain. And we've acknowledged that our understanding, while improving, is still incomplete, and in many ways inadequate to the challenge of fully comprehending these extraordinary objects. This is the nature of scientific understanding. It's not something that appears fully formed, completely correct. Rather, it develops gradually, through accumulated observations, through testing and refining theories, through careful work of many scientists over extended periods. We know more about magnetars than we did 30 years ago. In 30 years, we'll know far more than we know today. And in 300 years, our descendants will probably look back at our current understanding as charming but quaint, limited by the technology and theoretical frameworks we had available. This is how knowledge progresses. This is how the frontiers of understanding advance. And so, with all of this in mind, with a firm grounding in what we actually know about magnetars, and an honest acknowledgement of what remains mysterious, we're ready to turn our attention to a question that has probably been hovering in the back of your mind since we began this journey. What if a magnetar burst occurred near Earth? What would happen? What would be the consequences? This is where we move from the abstract contemplation of distant cosmic objects to considering how they might affect our own world, our own existence. This is where the cosmic becomes personal. This is where we ask ourselves what magnetars might mean for us. End